This is the pre-lab for experiment 6, where we're going to work through the theoretical calculations for the pHs of many of the solutions we're going to prepare in today's experiment. In part A 0.10 molar acetic acid solution is going to be prepared. The way that's going to be done is 5.00 milliliters of 1.0 molar acetic acid is going to be diluted to 50.0 milliliters. That dilution should produce a 0.10 molar acetic acid solution. The way we actually determine that or show that's actually true is with the dilution equation, MCVC equals MdVd. If we're going to solve for the molarity of the new diluted solution, we're starting with the concentrated solution that's 1.0 molar in acetic acid. We're using 5.00 milliliters of it, and then we're going to have a final volume, V sub D, of 50.0 milliliters. So working out the dilution, it turns out that the molarity of our acetic acid solution is going to be 0.10 molar. So theoretically now, what we're going to want to do is calculate what the pH of this acetic acid solution is. In the experiment today, we're going to wind up measuring it experimentally. And then we're going to add some strong acid, some strong base to that. We're going to theoretically calculate what the pHs of the acetic acid solution changes to with the addition of the HCl and the NaOH. And then we'll measure them experimentally. So the first theoretical calculation is just the pH of this 0.10 molar acetic acid solution. We've learned that if you have a solution that's a combination of a weak acid and its conjugate base, the pH can be determined more simply with the Hasselhoff equation. But this is not the case here. We don't have acetic acid and its conjugate base. We only have acetic acid. And when you have only one acidic or basic component in a solution, the only way to calculate the pH if it's a weak acid is to write the reaction that corresponds to its ionization, complete an ice table, and use its Ka expression. So to determine the pH of this acetic acid solution, we're going to write the reaction for the acetic acid molecule ionizing in water. Acting as a Bronsted acid, it gives up a hydrogen ion to water, forming the hydronium ion, which is what gives the solution its acidic properties, and the acetate ion. Now, initially, we know the solution is 0.10 molar acetic acid, but that molarity is going to go down because some of it ionizes, and we're going to algebraically figure out how much is left over, and similarly, how much hydronium and acetate ions are created. So initially, before any of this ionization reaction occurs, we have 0.10 molar acetic acid molecules, no hydroniums, no acetate ions. If it's a strong acid, of course, it would all ionize, but because it's a weak acid, we don't know how much ionizes, so we call that X. So X molarity of the acetic acid will ionize, it will form X molarity of hydroniums and X molarity of acetate ions. And if we add these columns, we then have the equilibrium molarities of all the species in the solution. Those equilibrium molarities are related to something called the equilibrium constant. It's the ratio of the molarity of the products to the molarity of the reactants. And if the chemical reaction is the acid ionization reaction, then the equilibrium constant is called the Ka. So the Ka for acetic acid will equal whatever the equilibrium hydronium concentration is, multiplied by the equilibrium acetate ion concentration, divided by the equilibrium acetic acid molecule concentration. If we look up the Ka for acetic acid, it's given on our class website, 1.8 times 10 to the minus fifth. That's going to wind up equaling the ratio of the equilibrium molarities, so x squared over 0.10 minus x. We've solved these before. We can ignore the x in the denominator because it's probably going to be a very small number. Simply solving this for x, we wind up getting 1.3 times 10 to the minus third. And because x is the hydronium ion concentration at equilibrium, the negative log of that is the pH. And so this is a 2 significant figure molarity. We're going to get a 2 significant figure pH when we take the negative log of this number. And so the theoretical pH of our acetic acid solution should be 2.87, and then we'll see how that compares when it's measured experimentally in the lab today. Now, theoretical calculation number 2 says what's going to be the pH of this solution if we add 1.00 milliliter of 1.0 molar HCl. So whenever we're mixing solutions together, it's way better to actually do the problem in terms of moles. And so what I'm going to do is I'm going to calculate how many moles of the acetic acid there were in that 50 milliliter solution, and then how many moles of HCl there are in the 1 milliliter solution, and those are going to be mixed together, so we'll know the number of moles of the two components. You calculate moles of a particular solute by going molarity times volume. So the solution we prepared here in part A is 0.10 molar acetic acid. We made 50 milliliters of it. So if I multiply its molarity times the volume of 0.0500 liters, that means I'm going to have 0.0050 moles of acetic acid in the solution. And then we're adding 1 milliliter of hydrochloric acid. So if I multiply its molarity times its volume, 1.0 moles per liter, multiplied by 0.00100 liters, we're going to wind up adding to this 0.0010 moles of HCl. Now, this is a strong acid. We know it completely ionizes, and if it does, we're going to get 0.0010 moles of chloride ions and 0.0010 moles of hydrogen ions, or more technically written correctly, hydronium ions. So our solution now, 0.0050 moles of acetic acid molecules and 0.0010 moles of hydronium ions. In our discussion of buffers, we know that buffers prevent a solution from changing its pH drastically because something in the buffer has to react with either a strong acid or strong base that's put in the solution. And in this case, we've put some strong acid into the solution. So what do acids react with? They react with bases. So to react away that 0.0010 moles of hydronium ions, our solution would need to have a base in it, and it doesn't. It only has weak acetic acid molecules. So the strong acid we put in here does not have a base to react with. This is not going to be a buffer solution then. So what happens? Well, the hydronium ions don't go anywhere. They stay in the solution. And so essentially the concentration of the hydronium ions in the solution will be the moles of hydroniums, 0.0010 moles of hydronium, plus the incrementally small number of moles of hydroniums from the acetic acid that ionizes, but that's going to be negligible. So we're just going to take the 0.0010 moles of hydroniums, assume that that's going to be the hydronium quantity in the container, and we're going to divide it by the volume of the solution. So the pH is just going to come from whatever the molarity is that we calculate of the unreacted strong acid in the solution, which is the 0.0010 moles, and we were mixing 50 milliliters and 1 milliliter together, so that means the volume of our solution is going to be 51 milliliters, or 0.0510 liters. So moles divided by liters will give me the molarity of the hydronium ions in this solution because they don't react away with anything. And if you know the molarity of the hydronium ions, you just take the negative log, and that's going to wind up being the pH of the solution. This is a 2 significant figure molarity, so the pH will be determined as 2 places past the decimal point. So our theoretical pH for the solution that we add the HCl to the acetic acid should be 1.71. The third theoretical calculation we're going to do is when we add 1.00 milliliter of sodium hydroxide, a 1.0 molar sodium hydroxide solution, to another 50 milliliter sample of our 0.10 molar acetic acid. So once again, we're mixing solutions together. I'm going to want to calculate the moles of the components that are in there. The acetic acid was 0.10 moles per liter. We had 50 milliliters of it, so when I multiply the molarity times the volume, I will again come out with 0.0050 moles of acetic acid. Now I'm adding to it instead 1 milliliter of 1.0 molar sodium hydroxide. I'm going to multiply the molarity and volume for that. Molarity 1.0 moles per liter, volume 0.00100 liters. This gives me 0.0010 moles of sodium hydroxide, which is an ionic compound that's soluble in water, which means when ionic compounds dissolve, they completely dissociate. So we're going to have 0.0010 moles of sodium ions and 0.0010 moles of hydroxide ions. Now that's a strong base. Do we have anything in our solution that can react away a base? And the answer is yes, we have a weak acid in here. So that sodium hydroxide, that strong base, does have an acid to react with. So this solution will behave in a sense like a buffer because it's going to be able to react away that sodium hydroxide. So anytime you have a strong acid or strong base that's going to be reacted away by a weak component in the solution, we can do the calculation more simply. Instead of with an ice table, we can use the amended Hasselhoff equation for this. Now the Hasselhoff equation requires us to know what the pKa is of our weak acid. So before I actually plug numbers into there, let's calculate what the pKa is. It's just the negative log of the Ka of the weak acid in our solution. That weak acid was acetic acid. Its Ka, you may remember from a couple of moments ago, was 1.8 times 10 to the minus fifth. So the negative log of that turns out to be 4.74, and with a guard digit 5. So if that's our pKa of the weak acid, the Hasselhoff equation is pH of a buffer solution equals the pKa of the weak acid plus the log of either the molarities or the moles of the weak base on the top and the weak acid on the bottom. Now, why are we doing the amended form? Because we're adding a strong component to the solution. In this case, we're adding a strong base, and bases react with the acids. So in the denominator, when I have moles of the acetic acid, it's going to be reacted away by however many moles of sodium hydroxide I put in there. So on the bottom, I'm going to go minus moles of hydroxide. What do the hydroxides do? They turn the acetic acid molecules into the acetate ions. So on the top, I'm going to go plus moles of hydroxide. And this is the amended form of the Hasselhoff equation when you add a strong base to a buffer solution. The pKa is 4.745. In the denominator of the parentheses term, the moles of the acetic acid is 0.00500. We're subtracting the moles of the hydroxide, 0.00100. On the top, the moles of the hydroxide are still 0.00100. Question is, what do you put in place of the moles of the acetate ions? How many acetate ions are in this acetic acid solution? The answer is essentially 0. So this sometimes gives students a reason for concern. I don't know what number goes there. Well, think about the solution. If it's just acetic acid and sodium hydroxide, nobody's put any acetate ions in there. You can have a 0 in the equation. That's perfectly fine. And in this case, it's perfectly correct. So the 0 moles of acetate ions are increased by 0.00100, while the moles of the acetic acid molecules are decreased by 0.00100. We can now calculate the second log term in there, add it to 4.745, and we're going to get the theoretical pH of the solution with the addition of that 1 milliliter of the 1.0 molar sodium hydroxide. I calculate 4.14. So in part A, we have the theoretical pH of just the acetic acid solution on its own. That should have been 2.87. The theoretical pH of the solution with a little bit of hydrochloric acid added to it should be 1.71. And now the theoretical pH with a little bit of sodium hydroxide added should be 4.14. And now experimentally, those solutions, their pHs are going to be measured. And they're going to be measured with a pH meter. The pH meter has a little bulb at the end of it, which in case it gets dried out, it's going to not work anymore. So it's always submerged in a buffered solution, which is contained in that screw top jar at the very bottom. If you unscrew that, that's going to expose the end of the pH meter, and that little bulb at the very end is a porous glass membrane that allows hydronium ions to pass through it. As the hydronium ions pass in and out, it changes the voltage that can be passed through the voltmeter, and there's a relationship between voltage and pH, and so it can actually measure the pH of a solution. Now, you have to actually calibrate it. Much like when we did spectroscopy, we had to make a calibration line between concentration and absorbance. Well, the pH meter needs to make a calibration line between pH and voltage. And so you'll see in the experiment today, to set this up, you're going to take the pH probe and you're going to place it into a solution of known pH. I think we're going to use a pH 4 solution first. When the pH 4 solution has the probe placed in it, then what happens is the hydronium ions flow across the membrane and they cause a certain voltage to become steady. When that voltage steadies out, you're going to record here what the pH of that solution is. We're going to use a pH of 4 solution, so we'll put 4 in here. And so the pH probe will know that this particular voltage corresponds to a pH of 4. We're then going to put the probe into a solution of a different pH. We're going to use pH 10. The voltage will change. We'll record the pH here of the second solution, which is 10. And now the pH probe is going to know this second voltage is corresponding to a pH of 10. And so the pH probe is going to make a calibration line. It's going to plot the 2 points you tell it. It's going to tell you that first point on the bottom left is the pH of 10, whatever its voltage is. And the higher point to the right is pH of 4, whatever its voltage is. And the probe calculates the equation of this line. So when you place the pH probe into any new solution now, it measures the voltage, and that's on the x-axis. It reads it up to the line over to the y-axis, and it tells you its corresponding pH. And that's how a pH probe winds up working. And so you'll test those solutions. We'll see how close the experimental values are to the theoretical values. In part B, we're going to prepare a 0.10 molar sodium acetate solution by taking 5.00 milliliters of 1.00 molar sodium acetate and diluting it to 50.0 milliliters. You could see how we get 0.10 molar for the sodium acetate if you go through your dilution equation again, but I'm not going to do that. And the first theoretical calculation now for part B is that we're going to want to calculate the pH of this sodium acetate solution theoretically. So how do we do that? Well, what's in the solution? Sodium acetate is an ionic compound, and ionic compounds completely dissociate when they dissolve, so therefore you're going to have 0.10 molar sodium ions and 0.10 molar acetate ions. Now, what's that sodium ion? Sodium ion comes from a strong base sodium hydroxide, so the sodium ion is a non-acid, doesn't do anything. The acetate ion comes from acetic acid, which is a weak acid, so the acetate ion must be a weak base. And if this is a weak base, that's going to react with water and it's going to create hydroxide ions, and you're going to have a basic solution. So we're going to calculate the pH from the reaction of the acetate ion acting as a base, and that reaction will have an equilibrium constant, and that equilibrium constant is called the Kb. So we're going to need the Kb for the acetate ion, and unfortunately that's not listed on handout 3 of the class website, but the Ka of its conjugate acid, acetic acid, is listed, and we know the Ka of an acid multiplied by the Kb of the conjugate base equals the Kw. So we can actually solve for the Kb of acetate if we know the Ka of acetic acid. That'll be 1.00 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5th. And so the Kb for the acetate ion is going to be 5.5 with a guard digit of 6 times 10 to the minus 10th. Now, this solution only has one component in it, the acetate ion. It's not a combination of a weak acid and its conjugate base, so we can't use the Hasselhoff equation. We have to do it the old-fashioned way, write out the reaction for what the weak base does, do an ice table, and then use its Kb expression. So when you have a base, bases, according to Bronsted, gain hydrogen. So a base, like acetate, will pull a hydrogen off of the water molecule to form an acetic acid molecule and create a hydroxide ion. Our solution initially is 0.10 molar in acetate ions, and we'll assume there are no products yet if the reaction hasn't occurred. And because it's a weak base, all of it doesn't react away. Some unknown amount reacts away, X, and it'll form X molarity of acetic acid molecules and X molarity of hydroxide ions. The equilibrium molarities will be 0.10 minus X, X and X, and those equilibrium molarities are related to the constant for this reaction called the Kb. Products over reactants molarities equals the Kb for the acetate ion. And we know the equilibrium molarities, and we just calculated the Kb a moment ago, so therefore 5.56 times 10 to the minus 10th must equal X squared over 0.10 minus X. Because the constant is so small, we know X will be a small number in this problem. I'm going to ignore the X in the denominator, and I can solve for X, which turns out to be 7.4 with the guard digit 6, times 10 to the minus 6th. X in this problem stands for the hydroxide concentration, so the negative log of that gives you the POH, which I get as 5.13. So the pH will be 14 minus that, and so theoretically we're going to predict that the sodium acetate solution that's 0.10 molar should have a pH of 8.87, and again, you'll measure that in lab today. Calculation number 5 is what is going to be the theoretical pH of this solution of sodium acetate if we add 1 milliliter of hydrochloric acid that's 1.0 molar. So once again, you're mixing solutions together. I would work in moles. So we're going to take the molarity of the acetate solution. It was 0.10 moles per liter, 50 milliliters of it. So we have a solution that contains 0.0050 moles of acetate ions. We're adding hydrochloric acid, so to get the moles, you multiply molarity times volume. 1.0 moles per liter, multiplied by 0.00100 liters, and that's going to be 0.0010 moles of HCl, which completely ionizes, and it's a 1-to-1 ratio, so 0.0010 moles of hydronium ions. This is a strong acid. Buffer solutions have something to react away strong acids. They have to have weak bases in them. So is there a weak base in this solution? And the answer is yes, there's acetate ions. That's a weak base. So we do have something in this solution that can react away our strong acid. And because of that, we can then use the amended Hasselhoff equation to calculate the pH of the solution and do this a little bit more simply. So to use the amended Hasselhoff equation, we need the pKa of the weak acid. Now, HCl is not a weak acid, acetate's not a weak acid, but in the buffer that would contain acetate, the acid would be acetic acid, and the pKa of acetic acid we had calculated earlier is 4.745. So we already have that number. So let's now go to the amended form of the Hasselhoff equation. In this case, we're adding a strong acid, so you have to ask yourself, what do acids react with? They react with bases. And that's what's in the numerator here, the moles of the acetate ions, that's the base. So that's going to be decreased by the number of moles of acid we're putting in there. So I'm going to go minus the moles of acid on the top, and it actually turns the conjugate base into the weak acid. So on the bottom, it's going to be plus the moles of the acid we've added. In the equation, the pKa is 4.745. In the numerator, the moles of the acetate ions are 0.00500. The moles of the hydronium ions that are reacting it away are 0.00100. Denominator, moles of hydronium ions, 0.00100. What's the moles of acetic acid in this solution? This was a solution of sodium acetate and HCl. We didn't put any acetic acid in there. That has to be 0. So now when you do the calculation, calculate the numerator, 0.00400 after you subtract them, the denominator, 0.00100 after you add them, take the log, add it to 4.745, and we're going to expect the pH of the solution with the addition of the HCl to be 5.35. Calculation number 6 is the theoretical determination of the pH of this sodium acetate solution if we add sodium hydroxide to it, 1.00 milliliter of 1.0 molar. So we're mixing solutions together, work in moles, calculate the moles of the species present. We have the acetate ions that were originally 0.10 moles per liter. Calculate the moles by going molarity times volume. You had 50 milliliters of the acetate solution, the sodium acetate solution. So molarity times volume will give me moles. So it's identical as what we did before, 0.0050 moles of acetate ions. And now we'll calculate the moles of the sodium oxide by multiplying molarity times volume. That turns out to be 0.0010 moles of sodium hydroxide, which dissociates completely in water. So therefore, it's going to be 0.0010 moles of hydroxide ions. That's a strong base. What do you need to react away a strong base? You need an acid. So is there another acid in this expression, in this solution anywhere? There's hydroxide ions and there's acetate ions. Well, acetate's a base. There isn't. So the strong base does not have an acid to react with. So if you ever wind up in a situation where we had earlier, where we had a lot of excess HCl in a solution, there was nothing to react it away, and in this case we have some strong base in the solution, there's nothing to react it away, there's really no major calculation to do. The strong acid, or in this case the strong base, do not react away. You just have to calculate the molarity of it that's in the solution now, and the negative log can give you the pH or the POH. So the pH is just going to come from the amount of this unreacted strong base that's in the solution, 0.0010 moles of hydroxide. Now the acetate ion, which is a weak base, will produce a little bit of hydroxides, but it's going to be such a small amount compared to 0.0010 that we're just going to ignore it. So we'll assume the hydroxide concentration in the solution is 0.0010 moles. Now what's the volume? We added 50 milliliters and 1 milliliter. It's going to be 51 milliliters. So divide the moles of hydroxide by the volume of the solution, and you will get the molarity of the hydroxides that are in this solution, 0.019 with the guard digit 6. The negative log of this number will be the POH, and the POH of the solution comes out to be 1.71. So the pH will be 14 minus that. So we're going to predict that this sodium acetate solution, when we add a little bit of sodium hydroxide to it, will have its pH increased up to 12.29. Part C, we're going to prepare a solution experimentally that's 0.10 molar in acetic acid and 0.10 molar in sodium acetate. This is significant because this is now going to be a solution that has both the weak acid and its weak conjugate base in it. It's going to be done by taking 5 milliliters of 1 molar acetic acid, 5 milliliters of 1 molar sodium acetate, and then diluting that up to a volume of 50 milliliters. That's where their concentrations become both 0.1 molar, or actually 0.10 molar. So the first calculation we want to do here in part C is calculation 7. What's going to be the theoretical pH of this solution? And because this is a solution that contains both the weak acid and its weak conjugate base, we don't have to write out a reaction for the weak acid or the weak base. We could actually do it for either of them. We don't need to write out an ice table, and then we don't need to use the Ka or the Kb expression. We can use the Hasselhoff equation to do this because the solution has both a weak acid and its weak conjugate base in it. So the Hasselhoff equation can be used. And in this case, I'm not mixing solutions together. I know the solution right now is 0.10 molar acetic acid and 0.10 molar sodium acetate. So I'm just going to use the Hasselhoff equation that's in terms of the log of the ratio of the molarities of the weak base to its weak acid. So the pKa is for the weak acid in this solution, which is the acetic acid. So that's 4.745, plus the log of, in the numerator, will be the concentration of the acetate ions, and because the sodium acetate is 0.10 molar, the acetate concentration will be 0.10 molar. And in the denominator will be the concentration of the acetic acid, which was 0.10 molar. You take actually the negative log of 0.1 over 0.1, that's the log of 1 just becomes 0, so therefore the pH of the solution just becomes 4.75, so that's going to be the theoretical pH of our solution, which is a mixture of acetic acid and sodium hydroxide. Then you'll determine experimentally today how close we are to that. Now, the next calculation is going to be the theoretical pH when you add some HCl to this buffer solution. I'm going to let you do that calculation on your own. And then the final one will be the theoretical pH when this buffer solution has 1.00 milliliters of 1.0 molar sodium hydroxide added to it. You'll calculate this one as well, and then you'll be able to compare each of the values you have to the experimental data we determined in today's experiment.